So when atoms or molecules absorb energy, that energy has to go somewhere. So they absorb it, and then it typically gets released again later, and it's often released as light energy. And we observe this in things like fireworks and neon lights. So this is a photograph of a neon light, and this is literally neon gas inside of a tube being excited by electricity. We've got fireworks. The light from the fireworks is caused by the heat explosions exciting the electrons in the atoms, and then as they return to their ground states, they release energy as light. So neon light, and then we can also make similar lamps with other elements. This is mercury and helium and hydrogen. And they give off different colors because the light that is emitted is at different frequencies. Each element emits a characteristic color. So when the light is passed through a prism, instead of seeing a rainbow, a continuous spectrum, we see a series of lines. It's called an emission spectrum. And it can be used to identify an element. It looks a lot like a barcode, or it can be used like a fingerprint. And this cannot be explained by classical physics. So here's what's happening. Here we have a hydrogen lamp where there's hydrogen gas inside of this tube, and it's excited by a voltage across it, and it releases light. And if we pass that light through a prism and separate it by its wavelengths, instead of seeing a rainbow like this one down here, we see 3 lines. And in between those lines is just blackness. Each of these lines has a particular color and a particular energy. So that's what hydrogen does. Helium looks like this. This is barium, oxygen, neon. And so the color that you observe from this lamp is the effect of these 3 colors for the helium. For neon, the neon light is very orange and very bright, and you see there's a lot of orange and yellow lines over here. And so that's what we perceive overall is those colors. You can also look at an emission versus an absorption spectrum. So this would be the emission, where you're exciting the element and it's emitting light. You can also look at what wavelengths of light can it absorb. And so then you're going to see dark spots or dark lines, exactly the same place that you saw the light. If you stick elements in a flame, that excites them and they can emit energy as light. Sodium gives a very bright orange-yellow flame. Potassium is kind of a purple, lithium's red, barium is green. And these are the things that cause the different colors in fireworks. It's different elements. A guy named Johannes Rydberg looked at these atomic spectra and came up with an equation relating the wavelengths in terms of small whole numbers, integers. And so it's really cool that he was able to do this, but it's not really all that useful because it doesn't explain anything. It just says, okay, here you can predict what's going to happen. So sometimes we make you do calculations with this. It might be easier to look at this as a vertical fraction. So 1 over the wavelength is equal to a constant times 1 over m squared minus 1 over n squared. So n and m are just integers, and he found that you could relate the wavelength in this way. We'll get back to that later when we talk more about the hydrogen atom. So review Rutherford's nuclear model of the atom. The atom has a tiny dense center called the nucleus, where almost all the mass of the atom is, and the nucleus is positively charged. And then we have electrons that are outside the nucleus, and the positive charge of the nucleus balances the negative charge of the electrons. The electrons are moving around in empty space. He didn't say what the electrons were doing, and that quantum mechanics is going to tell us more than we'd really like to hear about what are the electrons doing. Problems with Rutherford's model is electrons are moving charged particles. And according to classical physics, moving charged particles give off energy. So electrons should be constantly giving off energy. So the atoms should be glowing, but they're not. The other problem is if the electrons are always giving off energy, they should eventually run out of energy. They're going to crash into the nucleus, and the atom should collapse. But it doesn't. So the nuclear model doesn't explain what's going on here. So Niels Bohr, the guy who was quoted at the beginning of the chapter, developed a model of the atom to explain what happens to the structure of it when it undergoes energy transitions. Why do we see those three lines from the hydrogen lamp? So in his model, which is nice, his model is, we can get on board with this. Unfortunately, it's wrong, but it's nice. It's like the solar system. So the nucleus is like the sun, and the electrons are like the planets orbiting the sun. And they're going around in orbits, and we can picture this, and we're like, okay, I can go with that. That's great. The orbits are only at specific distances from the nucleus, just like the planets only orbit at specific distances, right? And the energy of each orbit is also fixed. It's related to the distance. We say it's quantized. So when something is quantized, it has certain set values and only those values. So our monetary system is quantized. If you look at paper bills, you have a $1 bill, the lesser known $2 bill. There's $5 bills, $10 bills, $20 bills. Have you ever seen a $15 bill? Or a $7.39 bill? They don't exist, right? They just don't. You can have $5, you can have $10. Now, can you put together a combination that'll give you $7? Sure. A $2 bill and a $5 bill. Or two $1 bills and a $5 bill. Or seven $1 bills. You can make 7 out of a combination of these other things, but you only have these bases, these specific amounts to deal with. Another example of something that's quantized is stairs versus a ramp. It's not exactly even, but so this is 1 foot, 2 feet, 3 feet. And then over here, we have a ramp going up the same. So if you're on these really lopsided stairs, you could be standing on the 3rd step, you're 3 feet off the ground. You could stand on the 2nd step, you're 2 feet off the ground. Can you stand there and be 2.5 feet off the ground? No, not unless you can levitate. Right? But on the ramp, you could stand here in the middle. You could stand anywhere along this. You could be at any elevation from 0 to 3 feet above the surface, right? So this is continuous, and this is quantized. There's lots of different examples. I tend to waste time talking about them. So the Bohr model of the atom, here we have the nucleus is like the sun, and then these are the orbits for the electrons. And as you get farther from the nucleus, the orbits are higher in energy. So when an atom absorbs energy, an electron can jump from whatever orbit it's in to a higher orbit. It can absorb the energy. Well, it's not going to stay there. It's eventually going to go back down. And when it goes back down, say from the 5th orbit to the 2nd orbit, it's losing energy that corresponds to the difference in energy between these two orbits. And that energy is released as a photon of light, and we can measure the wavelength. We can measure the energy of that light. So we can measure the energy difference between these two states for the electron. If it goes from the 4th orbit to the 2nd orbit, we see this blue-green light. The 3rd orbit to the 2nd orbit, we see the red light. Now there's lots of other transitions that are possible, but they don't give visible light. So from the second to the first, this energy amount is too small, and so it's going to be over here past red and we can't see it. So the distance between the orbits determines the energy of the photon of light that's produced. So the electron goes from one orbit to the next, and what's a little bit trippy is, unlike, when you go up the stairs, you actually go through space from one step to the next, right? But when an electron goes from one orbit to the next, it does not go through space. It goes from here to there without going in between. It's called a quantum leap. It doesn't seem possible, but that has to do with the wave-particle duality of the electron, that it can be in two places at once. But the energy of the photon is the energy difference between those two states. We can calculate that. The Bohr model works really, really well for hydrogen. Unfortunately, it doesn't work for anything else. If you have more than one electron, it doesn't work at all. So why do we even talk about it? Well, for one thing, we can visualize it. And even though it's wrong, it still is somewhat related to what we understand is correct. And it has a lot of historical importance, but it's been replaced by quantum mechanics.